Hello, everybody, and welcome back. We're going to talk more about mountain building today. There is a quiz that goes right along with this. I would pop that thing open on It's Learning, and you can knock it out as we go here. So what you're looking at there is a picture of my lovely wife and I on top of a mountain. How about that? Talking about mountains, and it's Hambling on a mountain. So Hambling's on a mountain. This is actually in Ireland, if I remember correctly. We hiked what's known as the 12 Bens. I think Ben is an Irish word for peak. I think sometimes they're called pins. I don't know. I'm pretty sure it means peak. But anyway, we hiked up into these mountains. It was amazing, crazy folded mountain range. We hiked all the way around, basically back what's behind me. We hiked around this huge loop of mountains around to the back of that and then down it. It was pretty good ways up, and as you can see, the clouds are right there just above our heads pretty much. It wasn't too much further up this mountain until we were actually in those clouds and having to navigate with map and compass because we couldn't see more than about 2 feet in front of ourselves because we were literally in the cloud. It was really cool. Lots of metamorphic rocks. We could see marble. Some of that white stuff on the ground is actually marble. Just beautiful countryside, just amazing, right? So let's talk a little bit about the different types of mountains and how they form. The first group of mountains we're going to talk about are known as folded mountains. So these are formed by a process. Well, actually, all mountains are formed by a process known as orogenesis, which is essentially it's the way that mountains form. It's the rising of mountains is kind of what the root of the word actually means. So orogenesis is the collection of processes that form mountains. Essentially, we classify the different types of mountains by the specific process that formed them. So the first group we're going to talk about here are folded mountains. And folded mountains, not surprisingly, are formed by folding. So these are typically mountains that are formed along convergent boundaries. So two pieces of Earth's continental lithosphere or oceanic lithosphere, or some combination thereof, collide and smash together and fold up these mountains. Okay, so folded mountains. Let's take a look a little further here. Here's a picture of some folded mountains, and you can actually see the way that the strata, the rock layers, bend and twist and torque kind of an up and down accordion sort of fashion. They really do almost look like accordions, the way they're folded up like that. Another group of mountains is known as fault block mountains. Now, fault block mountains are typically formed in rift valleys, so where plates are pulling apart, whether it's oceanic plates or continental plates, they're pulling apart. Now, that's pretty different than, let me just back her up a second here, a folded mountain. Folded mountains are formed when plates come together and converge, because you can imagine stuff crashing together is kind of crunching and crinkling up. In particular, two continental crust pieces colliding make big, big folded mountains, some of the tallest mountains on Earth. Fault block mountains, on the other hand, are formed when plates are diverging or moving apart. So we've got the Rift Valley in Africa. There's big faults there where blocks of rock have dropped down and blocks have been lifted up. And so you've got this big, deep valley and then these big, tall mountains that run along it kind of parallel to that. So fault block mountains, lots of them down in the oceanic rifts where the oceans are forming in the middle of the oceans, mid-ocean ridges. So these are called fault block mountains due to the fact that they're formed as these big blocks of crust get lifted and drop and are tilted along what are known as normal faults. Okay. Now there's two features that are associated with these fault block mountains. They're known as grabens and horsts. Heck of a word, huh? So the difference between these is pretty simple. The parts that sink down and fall downwards are known as the grabens, and the horsts are the elongated peaks that are have been pushed up. So a picture is worth 1,000 words on this one. Here we go. So you can see here the horsts are these long mountain range looking things, okay, and the grabens are the valleys that are between them, these big wide open valleys. So as the crustal plates are pulling apart, you can see the arrows there pulling from the right side and the left side. Blocks of of rock drop downwards and other areas get thrust up. And so you get this kind of a weird sort of a structure with these horsts and grabens. These are fault block mountains. Okay, let's talk domes and basins. So when there is uplift, when material is lifted up in an area, you can produce what's called a dome. And conversely, when it sinks down, you can get a basin. So domes don't necessarily even have to look like a dome on the surface if they've been eroded away. You'll just see these various rings of rock going round and round because of the erosion of the original structure. But that's known as a dome. These are uplifted type mountains. They're either circular or elongated sort of structures that are formed by uplift. Here's a picture of a domed mountain, and this is what it looks like with some of the material eroded away. So that central crystalline area there in the middle is actually older rock than the limestone plateau off to the side of it. So since it's been lifted up, that the bottom picture is a cross section there. You can see the granite and the schist, and then there's some limestone out there on the outer edges. But once again, like we talked the other day, the oldest material oftentimes is towards the center of this thing, where the uplift has happened, right? Now that doesn't always have to exactly be perfectly the case, like in some situations like this. I don't want to confuse you, but if that granite was formed because it was pushing upwards, the granite could very well be younger than some of that material on the outer edges where you see X and Y. But if you're to walk further out, like as you walk out from that central region, it's going to get younger and younger as you walk away from the center. Okay, that's a domed mountain. Look like big domes. Let's continue to talk about these convergent boundaries. Most mountains that we see on Earth's surface, on land anyway, are formed by convergent plate boundaries. I think that's a question on your quiz. A convergent plate boundary is when two plates actually collide, and there's these compressional forces, almost like just pushing and crinkling and pushing in, like think about pushing from two sides of a piece of paper, and everything accordions, it folds, it faults, rock metamorphoses. There's thick layers of sediment deposited sometimes at the edges of these land masses, but this is big mountain building right here. Some of the largest mountains that we know of are formed from these convergent boundaries, in particular continent-to-continent convergence. But let's talk about the different types of convergence and the types of mountains that they form along these boundaries. So basically any type of convergence can happen. The first one I've got here is ocean-to-ocean convergence. So we're talking about not the water so much, but the rock that's down underneath it there, right? So if you have two plates and they're composed of oceanic lithosphere, when they collide, you get a chain of volcanic islands along those collision points. Okay, so those islands are essentially mountains. It makes this big long range, and it can be right out there in the ocean, typically offshore someplace. If you have ocean-to-continental convergence, in other words, an oceanic lithospheric piece colliding with a continent, you get some similar features. You're still going to get sort of these volcanic mountains. Some of them may occur up on land. You might get some out in the water, but you're going to get some folded mountains on land as well from this. It also, when you have oceanic to continental convergence, you get another interesting feature known as an accretionary wedge. So all of the sediment and crud that's down there on the bottom of the ocean is getting rammed into the edge of the continent. And as it slams into the edge of the continent, it kind of gets scraped off as the plate descends, and it metamorphoses a little bit. This gives us some of these weird green schists that aren't really found anywhere else on Earth. But you get this weird kind of accumulation of sedimentary and metamorphic rocks that happens as the top of that plate is just literally scraped off as it descends. I'll show you a picture here. It'll make a little bit more sense. So this first one here is what it looks like when you have oceanic to oceanic convergence. So this will be a little bit easier to see. You've got two plates. When they collide there, one plate gets subducted or pushed down underneath the other plate. So this is like a time sequence from left to right. The subducting plate, by the way, and I think we mentioned this before, is always the older one. So the older it is, the heavier it is, and the cooler it is, the easier it is for it to get pushed underneath the other plate. And so you can see the subduction line zone there. As it melts and goes under, you get this whole chain of islands built up here along the subduction zone, basically, just off of it. And picture number 2 there is just further along in time. You see the volcanic island arc forming out there. Yeah, it's pretty much how it goes, oceanic convergence. Let's look at when an oceanic plate grinds its way into a continental plate. So the oceanic lithosphere is always heavier than the continental stuff. You can almost think of the continental stuff as being light and buoyant. It is, actually. It's not just a weird means of thinking about it. It truly is lighter than the oceanic crust. So the oceanic crust gets forced down underneath the continental stuff. And as it's pushed down, notice that yellowish region there that's called an accretionary wedge. That's the stuff that's being scraped off of the top of all that basaltic rock that is the oceanic lithosphere as it goes downwards. So it's like a bunch of mud and ooze and little bits of shells and stuff from the bottom of the ocean. And that stuff gets squished and heated and metamorphosed and becomes different types of rocks. As that plate descends, we're now going to get another volcanic arc. This one, however, is going to form up on land because where the plate's melting is underneath the land. And so those hot plumes of magma rise up and erupt out, and we get this whole volcanic continental arc right there. So that's an oceanic to continental convergence. All right, let's talk continental to continental. These are the big ones in terms of how tall the mountains get. This is the Himalayan mountains. These things can get humongous. So we're talking about the collision of two continents here. So originally, as these things are colliding, yeah, there's oceanic crust down there, and it's going to get subducted right up to the point where the two continents connect, and then these humongous folded mountains are going to form. Let's look at a picture. It'll make way more sense. These are responsible for some of the tallest and largest mountains on our planet. So here's India, and you may not know this. You might remember it from when we talked about Pangaea, but India just kind of trucked its way across the ocean there. And you can see in the top picture, as the ocean's shrinking because the oceanic lithosphere is being pushed down and underneath Tibet, India gets closer and closer and closer until in the bottom picture, wham, it slams right into Tibet. And those mountains fold and get thrusted up. And they're some of the tallest mountains on the planet, right? The Himalayas are famous. Big, big, tall mountains. They're still forming. They're still getting taller. But you see all the folding there. Notice also in the bottom picture, or I guess in the top picture to begin with, you see an accretionary wedge, right? You see that kind of being forced, all the stuff that's being scraped off there. And then finally it's going to form what's called a suture, where it's like stitched. Actually, one continent has been stitched onto another continent. So we can see these all over the world where this has actually occurred. So continental convergence. Let's talk about a divergent boundary. So there's other ways for mountains to form. It doesn't have to be collisions. They can also form when plates on the Earth pull apart. Now this is happening in places like the Rift Valley of Africa. It's happening all along the oceanic ridges all the way around our planet. And as these plates pull apart, blocks of plate material fall downwards, and some blocks are thrust upwards, and we get what are known as fault block mountains, and we already mentioned these. So along mid-ocean ridges, the most common type of mountain, which is going to be a question for you, is a fault block mountain. That's where you find the most of them. Okay. Now, there are a lot of other places you can actually find mountains. They don't all form just along plate boundaries. Okay, some mountains are formed by hot spots like Hawaii, lifting right up out of the ocean, right? Also, various forces of regional extension and stretching. There's other ways for mountains to form. By and large, most mountains are formed because of plates connecting or pulling apart, but that doesn't have to be the case. Let's talk accretion and terrains. So we mentioned this already, but if you have a foreign landmass moving across the ocean, since the plates move around, eventually it may collide with a larger landmass. And at that point, we refer to that process as accretion. So one landmass sticking, a foreign landmass, if you will, sticking onto another landmass. We have loads and loads of these all over the world. There's various regions of New Zealand that are exotic terrains. They're chunks that have been stuck onto New Zealand. They didn't originally come with it. Almost the whole of our west coast in America is accretionary pieces. They're exotic terrains that have been clumped on because as they moved across the ocean, they eventually stuck onto us. And we can tell that. We can tell that by dating the rocks, by looking at the type of rocks. We know they didn't form there in place. So the difference between an accretion and a terrain, accretion is the actual process of sticking these terrains onto other places, other continents. And there's a long history of this on our planet. Let's take a look here at how this occurs. So the process of this, you've got all these island arcs forming, right, as this subducting plate is moving along here. And eventually they get closer and closer and closer to the continental landmass, and then boom, they're sutured on. They get stuck on there. This is how much accreted terrain we have along the west coast of North America. Look at all that. Like, that's all foreign material that was stuck onto our continent as plate tectonics moved it around. Now, of course, people weren't around when this was, when this was happening. This is a very long, slow, like millions, hundreds of millions of years process, right? This is not a quick thing, but we can watch it still occurring today. Like, we know the continents are moving. We know they're eventually going to collide again. Probably have another supercontinent at some point where all the major continents are stuck together. Let's talk isostacy. So this is a principle that tells us that the Earth's crust actually behaves like it's floating on the mantle. It's almost like the material that we walk around with on the surface of the Earth, it's floating. So sometimes it floats higher, sometimes it floats lower. It depends on how heavy this stuff is. Okay, so essentially, isostacy is just the concept that Earth's crust is floating in a gravitational balance, because of gravity, on the material that's in the mantle. Now, and that's not liquid material, it's more of a silly putty kind of consistency, but it's still floating on it. Now, because of this thing called isostacy, when you get like crust that's thicker, okay, because mountains are formed, it makes the crust thicker in one spot. The crust will float higher. Okay, it also pushes it downwards deeper. I'm going to show you a picture here in a second and it will make a little bit more sense. Now, as crust material is removed, like off of a mountain, the mountain will actually lift upwards and float higher because you're making it lighter, right? And that process is called isostatic adjustment. So that's the process where you kind of establish a new gravitational equilibrium as those blocks are lifted up because you remove material off the top of them. Okay, so you just have to think about how heavy they are, and basically gives you an idea of how they're floating. Here's a picture of that. So if you think about blocks of wood floating on some water, the block in the middle there, there's a lot more block, right? So it's heavier, so it's sunk down a whole lot deeper. But because there's so much material, and it is lighter material, it does float the top of it higher than the rest of the blocks that are in the tank. See that? In the smaller blocks, they're lighter, so they don't sink as deeply down into the water. Now, what happens if you erode off the top of that high block, the long block in the middle? If you cut off some of that top block there in the middle, it actually readjusts and lifts upwards because there's a bunch of buoyant material underneath of it to lift it. So mountains, as they wear away, the material that's deeper inside the mountain lifts up and we can see it on the surface. And that's what we call isostatic adjustment. Here's another picture of some isostatic adjustment there, right? You've got the mountain range there. It's very thick, okay? As the mountain range wears away from erosion, the crustal material lifts up there in the middle picture. There's uplift. So that stuff that used to be deep, deep, deep at the bottom is lifted up towards the surface. Now that's important to us for a number of reasons. First of all, it allows us to see some deep stuff and understand how mountains actually form. That's helpful. But secondly, an awful lot of those rare minerals that we want to mine because they're precious are formed way deep down in that mountain range. And the only way to get to them easily is for the mountain to wear away, and then you can just access them without having to dig too deep into the mountain. So kind of neat how that works. Anyway, go ahead and finish your quiz, and you are done for today.